In this chapter, we will be using calculus as a tool in curve sketching. In this lesson, we will be using calculus to analyze asymptotes. We will begin, however, by looking at even and odd functions.
Alright, hi everybody. Now we're going to start a chapter on curve sketching. Now, in previous courses, up to this point here, you've probably, when you've sketched functions, sketched graphs and whatnot, in most classes the focus is on the x-axis and on how a function behaves around the x-axis. Okay? With calculus, we can extend our attention to other areas on the Cartesian plane, and we can fill in a lot more detail for the graph than you've been able to get up to this point. Now, although this lesson here today is going to be primarily about asymptotes, I'm actually going to start with just a little bit of a discussion of what we mean by even and odd functions here. Okay? Just to start us off here. And what I'm about to go through here isn't going to have a huge impact on how we graph things, but it is something that I'm going to need you to know as we go through this chapter. It applies here. You're going to get asked about it in this chapter, but where you're really going to see the benefit to understanding whether a function's even or odd is when we go to our last chapter on integration. Then you're really going to see where understanding this idea of even odd is going to be useful to you. But it does, strictly speaking, it does apply here in this context. Okay, so an even function, okay, are functions that satisfy the equation f of negative x is equal to f of x. Okay? In other words, when I substitute or when I replace the independent variable with its negation, the negation basically disappears. That is equivalent to the original function. Okay? These functions have a vertical line of symmetry through the origin. Okay? In other words, it's the y-axis. They are bilaterally symmetrical. Okay? They're symmetric about the y-axis there. And that actually makes a lot of sense, because when you think about what's going on here, when you plug a negative in for the independent variable here, that causes a reflection over the y-axis. And what we're saying here is that if you take the function and flip it over the y-axis, it looks identical to the original function. Okay, implying that sort of symmetry here. Now, it's an even function here. Take a look at the best example we can come up with. The easiest example is just the quadratic, y equals x squared. Okay? And notice that the exponent here is even. And what happens here when you've got y equals x squared, I can show you that this is an even function, because when I replace x with negative x, okay, when I do that in the function here, I'm going to take negative 2 squared. And we know that when we square a negative, we get a positive. Negative 2 squared is 4, and so is positive 2 squared. Okay? And you see that on the graph here. And what has happened here is that this has caused a reflection, and basically these 2 points have just swapped locations. Okay? Even, in this case, because the exponent is even. We're going to comment on that a little bit more in just a bit. It's not the only thing you got to consider here, but it's a good indicator. Odd functions are functions that satisfy this equation right here, f of negative x. We start with the same thing. We plug a negative in, but what that does here is that causes, or that is equivalent to the negative being in front of the entire function. Okay, these functions have point symmetry about the origin. Okay, or in other words, they've got a rotation symmetry about the origin of about 180 degrees. Now, just to see what's going on here, what this means here is when you reflect this thing about the y-axis, okay, that's the same as reflecting it over the x-axis when we put the negative in front of the entire function. Those two are the same. So this kind of a flip is equivalent to this kind of a flip. And actually, what that boils down to here is you can take this function and rotate it 180 degrees about the origin, and it will look exactly like the original function here. And the best example of this, the easiest example, is y equals x cubed. Okay? Y equals x cubed is an odd function, because if you plug a negative in, it's like putting a negative in front of the whole function here. And you'll see that here if you plug negative 2 into the function here. Negative 2 cubed is in fact negative 8. But negative 2 cubed is also the same as negative 8. Okay. Now, these are two very, very basic functions here, even degree, odd degree, but it's very easy to put these expressions together and create things that are actually neither odd nor even when you look at them. Okay, so just take a look at this little note here. For polynomial functions, an odd function must have an odd degree and an even function must have an even degree. And you can probably glean that from the examples that we just did. But this does not mean that all odd degree polynomials are odd functions, or that even all even degree polynomials are even functions. You could have other things happening there that keep your functions from obeying the rules that we use to define odd and even. So let's take a look at a couple of examples and you'll see what I mean. Okay, for our first example here, the question is f of x equal to 2 over x to the fourth? If you can't quite see that, that's x to the fourth plus 1. Is that even, odd, or neither? Okay, well, to determine what it is, what we do here is we're going to take and we're going to substitute in negative x for the independent variable. Now, what that does, when we plug that in, is we get this, 2 over, instead of it being just x to the fourth, it is negative x to the fourth plus 1. Now, what I've written here is wrong. Okay, this is incorrect. But this is what a lot of people do. And I just want to take this moment here really, really quickly to help you avoid this mistake here. Because bear in mind what I'm doing here. Okay, in the original function, it's x to the fourth, and then I replaced x with negative x, which means it should be negative x to the fourth. But that's not what this says. This is saying negative x to the fourth. And that's not the same thing. I want to be taking that negative to the fourth power as well. So to make sure that I do that, I have to put parentheses around that. This now tells me that I took the variable here and replaced it with negative x. Now it's this entire expression here, negative x to the fourth power. Okay? And when I do that, I know that a negative, okay, to an even power will become a positive. And so this is actually going to simplify to x to the fourth plus 1. Okay? And so notice that this is exactly the same as the original function. And so right here, this satisfies the restriction for an even function. So therefore I can say that f of x is even. Now let's take a look at the next one here. My next example is f of x equal to x cubed plus x squared, even, odd, or neither. And again, to check that I do the same thing, I'm going to take x in the expression here. I'm going to replace it with negative x. And again, bear in mind that in my expression here, in my function, the first term has me cubing the independent variable, and the second term has me squaring the independent variable. And now, in my function notation, tells me that that's supposed to be negative x, so negative x cubed plus negative x squared. Okay? And when I evaluate that, well, that negative, when you cube a negative, it stays negative. So this is going to become negative x cubed. But when you take a negative to an even power, it goes away, it becomes positive. So this becomes positive x squared. Now, notice that this isn't equal to, okay, that's not equal to f of x, but it's also not equal to negative f of x. Okay? This is a little different. Although the negative is out front, okay, it's not the same thing as this. Just having a negative in front of an expression doesn't mean that the whole function here is negative. And that's what this is saying here. If I was to factor out that negative and try my hardest to make it look like negative f of x, this would become negative x cubed. But you would have to factor the negative out of both terms, and that would cause this to become negative x squared. So that these two expressions here are exactly the same. If you multiply this negative through, again, it takes you right back up to this step right here. It would be great if this was exactly the same as the original expression. Then it would be equal to negative f of x, but it's not. So as a result, okay, f of x is neither odd, whoops, nor even. Okay. Now that means that this graph is not symmetric about the y-axis. It's also not symmetric about the origin by 180 degrees. Now it might have other symmetries to it. Okay, not denying that, but it certainly doesn't have the two symmetries that we associate with being either odd or even. Okay, now let's start talking about asymptotes. And we're going to talk about vertical asymptotes to start off with. You have probably had some experience with this in a previous course. Now what we're going to do is we're going to use some tools that we've learned in this course to look at vertical asymptotes just a little bit more closely. So remember, a vertical asymptote, what this is a vertical line that a function approximates for large values of y. Now the absolute value of y. Meaning that what I'm looking at here is when you look at your coordinate plane, okay, for a vertical asymptote, I'm looking at how the graph behaves when I go up really, really far or I go down really, really far. Okay? So I'm moving quite a ways away from the origin and I'm watching the behavior of the function as this happens. If the function starts to get closer and closer to a very specific line, that line is what we would call the asymptote. Okay? Now, vertical asymptotes are typically the result of the non-permissible values in a rational function. That's what you're seeing right here. Okay. Now, as a result, that means that you cannot cross, okay, you cannot cross a vertical asymptote. It's a mistake, though, to think that you cannot cross an asymptote at all. No, the vertical one you can't cross because it's the result of not a non-permissible value. Okay, if I say in a function here that x can't be 1, okay, then it's not possible for me to have the graph cross that vertical line because there's that restriction. X cannot equal 1. If it did cross that line, then obviously somewhere it did equal negative. The x value was allowed to equal 1, so we can't do that. That's how a vertical line is defined. Vertical asymptote is defined here. Now, let's take a look at an example, and we'll use some calculus here, some of the tools that you've learned in calculus, to investigate it a little bit further. You'll see what I mean in just a moment. All right, so now this question says, investigate the behavior of the function y equals 1 over x squared minus 1 near its vertical asymptotes. Okay, well that's straightforward enough, but the first thing we got to do is figure out what its vertical asymptotes are. And that's as simple as determining its non-permissible values. Okay, so first of all, we're going to take a look at that function. We're going to factor the denominator. And that's actually relatively easy because that's a difference of squares. So x minus 1, x plus 1. Which tells me right away that x cannot equal plus or minus 1. Now, okay, these are what we would call essential discontinuities. I am stuck with them. This is the most simplified form, or sorry, I should say, this is the most simplified form that this expression can get to, and it still has non-permissibles in it. So that means these are essential discontinuities. They are a necessary part of this function. For you to understand how it behaves, I need to see those things. They're not going away. So I know that they're there. I know that this graph has vertical asymptotes at plus or minus 1. Now let's use limits to see if we can figure out what's going on with this function here. Now, first of all, let's take a look at negative 1. So what I'm going to do here is I'm going to use the limit as x approaches negative 1 from the left, okay, of 1 over, and I'm going to use the factored form here, x minus 1, x plus 1, to see what's going on here, how it behaves. Now, just a little bit of a heads up here, because this is a vertical asymptote, when I do some work like this, essentially there can only be one of two answers here. I'm either going up to positive infinity or down to negative infinity. That's it. There can be no other answers if I've identified that these are vertical asymptotes. So let's just see what's going on here. If you approach negative 1 from the left-hand side, and let's just take a quick look on the number line right here. So here's 0. Okay, here's negative 1, negative 2, positive 1, positive 2. On the number line here, if I approach negative 1 from the left, so I'm running through a series of numbers to the left of negative 1. If I subtract 1 from that, that puts me over here really, really close to negative 2. Okay? So if I approach negative 1 from the left, I am essentially approaching, okay, negative 2 right here. Well, that's not a problem. It's not a problem at all. If I if I take negative 1 and I approach from the left and I add 1 to it, I'm going to approach 0. Now, I know that I can't divide by 0, so I know that's going to lead to an undefined. Okay, that's good. That's exactly what I want to see here. But what I want to know is I want to just have a little bit more information. Is that going like infinitely up? Like undefined in this context, it was implying an infinity here. Okay, and the reason why that works here is because infinity really isn't, it's not a real number. Okay, and that's why we can interchange it with this phrase undefined. But if I approach negative 1 from the left and I add 1 to it, that means I'm approaching 0 from the left. Which means every time I evaluate for this little factor right here, my result is going to be negative. Now this is going to look a little goofy, but it is going to help me figure this out here. I'm going to put a negative in front of that 0. Now 0 can be neither positive nor negative here, but just to understand here, this is a limit. I never actually get to the number negative 1. Never do. I've always got a non-zero number here. But because of the way the limit works, I get so close to 0 that it's essentially 0. It's going to behave like the 0 here. But it's not the 0. And not only is it not 0, it's slightly on the negative side. So I've got two negatives here. They're going to cancel out. This is going to become positive infinity. So what that means is on the left-hand side of negative 1, the graph is going to shoot off to a positive infinity. Now let's take a look. What happens when I approach negative 1 from the right? Well, if I approach negative 1 from the right and subtract 1, I'm still getting closer and closer to negative 2, and that doesn't cause me a problem. I'm totally fine with approaching negative 1. But if I approach negative 1 from the right and add 1 to it, now remember, I never get to negative 1. I'm approaching it from this side, and if you add 1 to it, that means it's like I'm approaching 0. I'm approaching 0, but I'm approaching it from the positive side now. So I'm dealing with a whole bunch of numbers right here, and every time I pick a number here, I add 1 to it. That's what this expression right here does, x plus 1. It's going to give me a whole bunch of positive values, really, really small positive values, very, very close to 0, but not 0, still a positive number. Now, the overall result, again, is going to be to push me to an infinity. That's what the nature of these numbers are when I approach 0. But because this is negative and this is positive, this is going to drop down to negative infinity. So in other words, as I approach negative 1, okay, as I approach negative 1, from the left-hand side, the graph is going up to infinity. From the right-hand side, it's going down to negative infinity. Now let's switch our attention over to positive 1. So as x approaches positive 1 from the left, x minus 1, x plus 1. As I approach positive 1 from the left, very first thing that my expression tells me to do is subtract 1 from that. But as soon as I do that, I create a bunch of numbers that approach 0 from the negative side. So this becomes negative 0. And again, I know that doesn't make a lot of sense. I'm just using this as, just writing that down as a way for me to understand what's going on. This x plus 1, if I'm approaching 1 from the left, if I add 1 to it, I simply approach 2. And that's not causing me a problem at all. 2 isn't the issue, it's the 0. Notice though that I've got a negative down here and a positive down here. The overall result is going to be negative, But because one of them is getting closer and closer to 0, the overall result is going to go down to negative infinity. Okay? So again, I'm going to have this asymptote here at 1, and from the left-hand side, it's going to go down to negative infinity. Now, you can probably guess at this point what's going to happen on the right, but let's go through and talk about it anyway. So I've got the limit as x approaches 1 from the right of x minus 1, x plus 1. Now let's take a look at x minus 1. If I approach 1 from the right, so I'm moving along the x-axis, getting closer and closer to 1, but from the right-hand side, if I subtract 1, I'm going to be approaching 0 from the right, which means I'm approaching 0, but I'm approaching it with a whole bunch of positive values. X plus 1, on the other hand, is going to put me just slightly over 2, which means I'm approaching 2. But again, 2 isn't a problem. It doesn't matter if I'm approaching 2. Okay, 2 isn't causing me an undefined result. So 2 is okay. It's this 0 that's the problem here. But because both denominators are positive, the result is going to be positive infinity. So from the right, my graph is going to go like this. And so now you've got a pretty clear sense of how this particular function, or this one right here, approaches its vertical asymptotes from the left or the right. Okay, so remember, what we do here is we identify what the asymptotes are, and then we simply take the limit as you approach from the left or the right of each one of those. Just notice which of those terms is going to 0 and which direction it's doing that from. Is it doing it from the positive side or the negative side? I promise you a number line really, really helps clarify that. Okay, now let's take a moment and just talk about horizontal asymptotes. This is a horizontal line that the function approximates, and I use that word approximates, for very large values of the absolute value of x. So once again, what I'm referring to is the way the graph behaves when you get really, really far away from the origin. Okay? By the origin, a lot of graphs are bouncing around, they're jiggling, they're scribbling all over the place here, but what we're seeing here is that in a lot of cases, the further away you move from the origin, things start to settle down. Its behavior starts to smooth out. And that's what we're asking about here. When the behavior starts to smooth out, what is it doing? And in some cases, what we see are there's these horizontal lines that appear that the graph seems to be attracted to. Now, when it comes to vertical asymptotes, these are the result of non-permissibles. That's not necessarily true for a horizontal asymptote here. Now, and just to be clear, when you approach a vertical asymptote, remember that that's the result of an undefined value, meaning you can't cross it. But a horizontal asymptote doesn't have to work like that. Here's a horizontal line. I could have an asymptote that does that. That simply, whereas as the x gets larger, it just approaches that line. But it could also do this very easily. It could cut right through it and then come back up and then swoop down like that. In fact, it could also do this. It could come and it could actually bounce back and forth across it like that. In fact, it could cross it an infinite number of times. You see this kind of a sort of a trigonometric sort of a curve here where it's like sinusoidal, but the graph is being pinched in towards the line. And actually, for those of you that go on and study like differential equations at university or physics, you'll recognize these graphs here. These graphs are related to damping effects. So just really quickly to give you a context, when you've got a car, you're driving a car and you've got its struts there, I can't think of the word right now, but anyway, when you hit a bump, okay, what happens is we get a compression, and the car goes past the shocks get squished, and when regular shocks should expand out past its steady state, okay, past not moving, and then slowly come back up. Now, if it doesn't, if they squish and then slowly move back towards its steady state position, if you hit another rock somewhere in here and causes it to squish again, you'll hear it crunch into the metal frame of the vehicle. That's horrible. On the other hand, if you got your shocks are doing this and they compress and then they open up and they do this, well then the car starts to bounce around and it's, but it looks really goofy here. The car is just having a great old time driving along. If you're still feeling that bump like half of a block away, there's probably something wrong with your shocks there. We use infinite limits to determine the presence and behavior of the horizontal asymptote. Okay, so let's take a look at an example so you can see what I mean by this. Okay, let's investigate the long-term behavior of that function. And we've looked at this function before, but let's look at it again. 1 over x squared minus 1. Okay, so what we're going to do here to figure out the long-term behavior, to look for the horizontal asymptotes, is we're going to take the limit as x approaches either positive or negative infinity, okay, of 1 over x squared minus 1. Now, sometimes there is a difference when you're going positive infinity, negative infinity. And in fact, if you recall, you will remember functions that we looked at way back when we were looking at limits, functions that behave differently when you go quite far to the right or quite far to the left here. This particular function actually won't have that problem here. Now, let's take a quick look at this. What I'm going to do to understand the long-term behavior of this graph here is I want to create some zeros here. So I'm going to take the highest degree in the numerator and I'm going to multiply the numerator and denominator by 1 over the largest degree in the denominator. So what I'm going to get here is this is going to become the limit as x approaches positive or negative infinity. My numerators are going to become 1 over x squared, and then my denominator will become 1 minus 1 over x squared. Now, what that has done for me, if I now if I now apply the limit as x goes off to either positive or negative infinity, and I hope you see that because of the square, it doesn't matter. The numerator will become 1 over infinity, or 0. But the denominator will become 1 minus 0. And so I will get 0 over 1, which is just 0. Which means that my asymptote will then be the line y is equal to 0. Okay? And I hope that makes sense. Okay? That's the line that this is approaching as we go forward and backward if I go to the right and to the left on the Cartesian plane. Basically, the x-axis is becoming my horizontal asymptote. Now, I didn't actually have to do it this way. I can actually see that from the original. Because the degree of the denominator is larger, when I let x go off to either positive or negative infinity, the denominator here is going to dominate in this term. And because the denominator is dominating the value of the term, it's going to automatically go to 0. Sorry, one more thing before we leave this here. Another thing that you might notice, and it becomes relatively clear right here. This expression right here is going to go to 0, but this little expression right here is always going to be positive when it does so because of the square here. The denominator, remember, this is also going to approach 0. It's going to get really, really small. But this is going to do it by positive values. So I'm going to be subtracting these small values from 1. This is going to be positive, and this is going to be positive. So what I'm trying to get at here is I am going to approach 0, and it doesn't matter which direction I go, right or left. I'm still going to be approaching 0, but I'm going to be approaching 0 through positive values, meaning that I'm approaching this asymptote. Okay, I'm approaching this asymptote of y is equal to 0 from above. Okay, so I am going to be going down. So if I look at my graph here, to the left and to the right, I'm going to be doing that, coming down to my asymptote from above. Now, you don't really need to use this kind of an analysis to figure that out. In most cases, once you start to apply some calculus, to looking at the behavior of the graph here, that sort of behavior will become obvious. In fact, you'll notice that it couldn't be any other way. And you don't really need to apply this sort of thinking to figure that out. You do need to use the limits there to figure out what the asymptote is, but when it's horizontal, how it approaches that asymptote will be clear because of other information that you've discovered. Okay, now just to finish off this previous couple questions here, kind of put them together. Now let's try to sketch the graph of y equals x squared minus 1 based on the above information. Now, we should note that if I let x equal to 0, my y-intercept is negative 1. So let's just put this together here. So here's my Cartesian plane. Here's negative 1, 1, positive 1, down here negative 1, negative 2, positive 2, and so on. I know that I've got asymptotes here at negative 1, positive 1. Oh my goodness, I got this little curve to it. Whatever. I know that as I go to the left, I approach 0. To the right, I approach 0. There's my horizontal asymptote. I know that from the left of negative 1, I go up to infinity. To the right, I'm going down to negative infinity. This was going down to negative infinity and up. And I know that's going to go through negative 1. So that information right there should be enough for you to realize that, oh, this must look something. Oh, I did that kind of poorly, but anyway. Like that. Has to. Okay? So let's just give you an idea of the usefulness of limits when analyzing these kind of asymptotes. Now let's take a look. Okay, so let's just summarize really quickly what it is that we've just looked at. So summary of asymptotes here. If we have a rational function, and it's important that we state that because asymptotes really don't occur if you don't have a rational function. Okay, so it's got to have a function that's got f of x divided by g of x. Then we have the possibility for asymptotes. Now here we go. Vertical asymptotes, if f of x and g of x are relatively prime, meaning there's no shared factors. Okay, so it's not like you've got like an x minus 1 in the numerator, x minus 1 in the denominator. That sort of thing isn't happening, okay? Then for all a such that g of a is equal to 0, and remember that g is the denominator, so whenever the denominator goes to 0, that x equals a is going to be my vertical asymptote. Okay, this is called an essential discontinuity because it's a persistent feature of the graph. It's not something that I can kind of just play with and get rid of. Even after simplifying, I'm still stuck with that non-permissible. Now, on the other hand, if f of x and g of x share a binomial factor, let's say x minus a is common to the numerator and denominator, then the rational function will have a hole at x equals a. In other words, you'll have this little line here, and it goes like this. Now, you should have talked about this in a previous course. So I should be going over old ground here. But what's going to happen here is if you've got x minus a in the numerator and the denominator, I can cancel those factors. At least I can cancel them so long as x is any other number, so long as the variable takes on any other value except a. Because when you've got x minus a over x minus a, sorry, that's a, these two will be the same number for whatever value of x you choose. So you could choose it so that it becomes 5 over 5, 10 over 10, 20 over 20. But as soon as it becomes 0 over 0, that's non-permissible. You're not allowed to do that. And that's why when you cancel it, yes, it cancels. Yes, it becomes a 1. That ratio becomes a 1. But in that one little instance, when the x-coordinate becomes a, there's a hole there. There's a gap in the graph. This is why we call it a removable discontinuity, because by factoring and simplifying, you can essentially get rid of the problem. Okay? But to be technically correct here, you do need to identify that little hole that is left over in the graph. Now, to determine the behavior around an essential discontinuity, and that's going back to our vertical asymptote, what we're going to do is we're going to use left and right hand limits to investigate what happens as we approach a from the left and a to the right. And again, the results will only ever be positive or negative infinity. And so that kind of helps you as you noodle it through. You already know it's going to go off to an infinity. There's an undefined there. You merely have to determine where the positives and negatives are. With a horizontal asymptote, if f of x has a degree less than or equal to the g of x, okay, then the function will have a horizontal asymptote that can be determined, okay, by taking the limit as x approaches infinity. So essentially, if the numerator has a degree that's either less than or equal to the denominator, you're going to have a horizontal asymptote. If you don't, okay, if the degree of f of x is larger than the denominator, then what happens here is the numerator, okay, maybe you've got like a cubic, you've got a cubic over a quadratic. Well, as the x values get bigger, a cubic will get bigger much, much faster than a quadratic. And so what happens is the cubic basically dominates the value of that rational expression. Now, on the other hand, if the degree of f of x and g of x are the same, okay, and that's really all that matters is the degree. The coefficients, okay, aren't going to affect this when I say that if they're the same, then they're going to grow at the same rate, basically. So then, wait a second, are the same because of the presence of a radical. Oh, I'm sorry. I forgot about this little note here. Sorry. If they're the same, then it's just the ratio of the leading coefficients. We'll talk about that in a second here. But I forgot about this little note, and this is an important little note here. If they're the same because of the presence of a radical, then that radical actually introduces two possibilities for the horizontal asymptote, and it changes if you go to the right or the left. Okay. Normally, if you've got two different functions here and you've got the same degree, so let's say you've got a x to the m plus dot dot dot, doesn't even matter, then you've got b x to the m plus dot dot dot. If the degrees of the numerator and denominator are the same, then your asymptote is going to be y equals a over b, just those ratios of the leading coefficients. Okay. If the degree is less, if you've got a, let's say, x cubed plus dot 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 over b x to the fourth dot dot dot, then it's simply going to be y is equal to 0 because the denominator, the expression here will dominate. Okay. So, and again, these are rules that you would have looked at much, much earlier in the course. But this is the one that we want to take a look at right now. What happens when a radical causes the degrees to be the same in the numerator and denominator? Whoops. So let's take a look. So if you've got the square root, let's zoom in a little bit here. The square root of 9x squared minus 2x plus 1 over 2x plus 4. So notice that the degree of the numerator and denominator, they're both 1. Okay, that square root is going to create an expression that's got a degree of 1. So that creates a little bit of ambiguity here, but it's not hard to get around. Essentially what's going on here is this. When you get really, really, really big values for x, then in the numerator, these little guys here don't matter. Just like in the denominator, this plus 4 doesn't matter. If x is, like, let's say, if x is already into the billions, well, 2 times a billion is 2 billion. Plus 4? Does the plus 4 really do anything to change that value? Well, no. I mean, if you had $2 billion and somebody offered you $4, would you care? Well, no. Okay? And that's sort of what we're getting at here. When the values of x get really, really large, then these other terms simply don't matter. And so now the numerator can be simplified down to be 3x and the denominator becomes 2x. Except for one little detail. Because I'm taking the square root here, this is always going to be the principal square root. Okay, whoops, and that's my horrible handwriting. The principal square root. And the reason I bring that up is because it's always positive. So when I take the square root of this thing, it will be positive. Okay, necessarily it'll be positive. So whether I let x get big in the positive direction or big in the negative direction, that numerator is going to be positive. Because that doesn't exist in the denominator, that 2x will be positive or negative depending on which way I go. So if I let x go off to positive infinity, okay, what happens here is my numerator becomes this positive expression, 3x over 2x. The x's cancel here. Yeah, they do. And so you're left with this 3 over 2 ratio here. But bear in mind that this was always positive. But 2x could be either positive or negative depending which direction you go. So as you go to the right, the numerator, always positive. The denominator is going to be positive as well, so the ratio is positive, 3/2. If you go to the left, okay, bear in mind that the numerator is going to become this 3x, but it's forcing it to be positive. But the 2x in the denominator will end up being negative because of the x. Now, those values of x's cancel, but the sign stays. Okay, the sign stays. And so this becomes a negative value. I know that's a little hard to kind of get your head wrapped around, but even if you graph that, you'll see it happen. Okay, use your graphing calculator, you'll see exactly what I mean popping out here. And that really is the reason why. Okay, that square root up there is spitting out a positive value. The denominator doesn't have that restriction, so it can be positive or negative depending which direction you go. So this graph here, okay, if you were to plot that, it's going to have an asymptote up here at positive 3/2 and an asymptote down here at negative 3/2. It's essentially going to look something like that. Okay, I hope that makes sense. All right, so let's just do one more question here. We're going to find all the asymptotes of this expression, y equals x plus 1 over x squared minus 5x minus 6, and we're going to sketch the function here real quick. So the first thing we're going to do here is let's look for because it's a rational expression, let's look for the vertical asymptotes. And so we do that by factoring. So x plus 1 over, and we will get x and then factors of 6 that add to that negative 5 there. So it's going to be, what do we got here? Negative 6 x plus 1. And right away I see that my numerator and denominator are not relatively prime. They actually share this factor of x plus 1. Now, that means that I can cancel that out, x plus 1 over x plus 1. But that is not equal to 1 over x minus 6. These are not equal. Now I'm using the equal sign right here, and technically I probably shouldn't. Technically it should probably have a little bit of a wave to it like that, approximately equal to, because these two expressions are not equal to each other. If I plug negative 1 into this, okay, the original, I get 0 over 0 because of the terms that I canceled, and that's undefined. But if I plug negative 1 into this, I get 1 over negative 1 minus 6 is 1 over negative 7. That's okay. So negative 1 causes a problem here, but it doesn't cause a problem here. So they're not equal to each other. They're only equivalent. Now, I can make them equal to each other by simply including the restriction that x can't equal negative 1. And that right there is the essence of the removable discontinuity. By canceling, I've gotten rid of the part of this thing that actually is undefined. Now, in order to maintain equality, I actually have to state that. This is in a simpler form, but they're not equal until I write this restriction there. And actually, that gives me right there that hole. Okay? That hole in the graph, and I've already figured out what it was. If I plug negative 1 into this looks like it should have no problems. It should just be negative 1/7. But I know that that doesn't work, that particular point that really does exist on this graph, because of this function, has been popped out. It no longer exists there. Now, here, the essential discontinuity, okay, the essential one is going to be x cannot equal positive 6. That's the one I'm stuck with, and that's my vertical asymptote. Now let's take a look what happens with it. If I approach 6 from the left of 1 over x minus 6, now let's think about what's going on in our number line here. Okay, so I'm approaching positive 6 here. So here's 0, here's 6. If I approach 6 from the left, oh, sorry, I meant to do it like that, put the negative up top there. If I approach 6 from the left and subtract 6 from it, I'm going to be approaching 0 from the negative side, which means this is going to go down to negative infinity. And likewise, if I have x approaching 6 from the right, I'm up here, and x minus 6, I'm going to subtract 6 from that value, I'm going to be right here. I'm going to be approaching 0 from the positive side, in which case this thing will go off to positive infinity. Because remember, those are my only two results. They're either positive infinity or negative infinity. I just got to see, after doing my, looking at my limits here and applying the operation in each of these little factors here, am I getting a positive value or a negative value? Now the last thing that I want to do here is figure out my long-term behavior here. So I'm going to take x and I'm going to approach positive or negative infinity here of 1 over x minus 6. It doesn't really matter to me whether I go positive or negative infinity with this one, because just watch what happens. Because the degree of the denominator is larger than the degree of the numerator, the denominator will dominate the long-term value of this function, which means it'll get larger much faster than the numerator, which means this whole thing is going to go to 0. Okay? And so I'm going to get a horizontal asymptote of y is equal to 0. Now, based on all the other information that I've got here, I can kind of figure out whether it's approaching it from above or below. But just for out of curiosity's sake, let's take a quick look at it. So here's my number line. I'm going off to positive infinity or to negative infinity. Let's go to positive infinity first. If you let x become really, really large positive number, then x minus 6 is also going to be a positive number. And so the whole expression is going to be positive. So when I go to the right, I'm going to be coming down to the asymptote from above. But if you approach negative infinity, and so x is this really, really large negative number, and you subtract 6 from it, it's still going to be negative. So the overall value is going to be negative no matter how far you go to the left, meaning that I'm going to approach 0 from the negative side of it or from below. So now that gives me a sense of the behavior of the graph here. Let's put everything together. Okay, I know that I've got a hole at negative 1/7. I know that I've got this asymptote over here at 6. Okay, I know that from from the left I'm going down to negative infinity, and from the right I'm going up to positive infinity. Oh, did I get that backwards? Oh, I'm sorry. I know what I got wrong here. Oh boy, I bet you there's a bunch of you responding to that as soon as you saw it. That's not where negative 1/7. Negative 1/7 is right down there. Okay. Oops. Sorry about that. And then I'm approaching the asymptote here from below and the asymptote here from above. So the graph's going to look something like this. Goes through there, then it's going to drop down, and then here it's going to go like this. Sorry, little mistake. I forgot that the y coordinate was negative there. And there you go. That's what that function is going to look like.